All right, good morning. So over the last couple of decades, this increasing interest in the serpentinization reaction has led to a lot of new experimental work and really a boom in experimental work as well as some theoretical studies. And I think these studies are changing our view of what the serpentinization process is and what it can produce. And today I'm going to share with you some of that stuff from an experimental perspective mostly. And so before I proceed, I should note that some colleagues who've contributed to this, Friedrich Klein principally has contributed a lot of thinking on this, but also a whole host of other people that have helped with analysis and thinking about this thing have contributed to this. So, what's that? I'm never sure whether I'm Grandpa or Mr. Burns. I think I started out as Homer, but I think I've evolved. But this is Frieder right there. I'm pretty sure about that. So I think everybody is pretty familiar with this serpentinization reaction, where you take an ultramafic rock, react it with water, make this rock called serpentinite. And of particular interest to a lot of people in astrobiology is the byproducts that may include hydrogen and methane. And I really wanted to make the point, though, that these ultramafic rocks that are the starting point of this are really the large fraction of mass of most solid body planetary bodies in our solar system, particularly bodies that have differentiated. And even these icy moons are going to be, most of their mantle, so to speak, is going to be made of these ultramafic rocks. So there's good reason to think that this process is going to be very widespread in the solar system. So most often we see this reaction oftentimes expressed in this simple way, where you have olivine plus water reacting to form this suite of secondary minerals, serpentinites, which include serpentine, magnetite, and brucite, and producing hydrogen. Well, if it was really this simple, then my last decade of my life would have been a lot easier. But it's very complicated. And some of the complications to this reaction come in to this as illustrated here, in which we not only have olivine reacted, we also have orthopyroxene reacted, and how these two different reactions contribute to the process can cause a lot of different reaction pathways to go on. And the other factor that comes in is when this process happens, the iron can get distributed in many different places in these minerals and in different oxidation states. So there's what's emerging here is that there's a lot of different reaction pathways that can go on during serpentinization. It's not just this one simple reaction. And for those of you who are not familiar, so the generation of hydrogen in this process occurs when some ferrous iron from these reactant minerals reacts with water to become ferric iron and gets distributed in these second minerals, producing hydrogen. So what happens to the iron in this process has a lot to do with how much hydrogen is getting produced. And understanding how that happens, how it gets distributed, is really been a focus of both my research and research of others in recent times. So I'm going to be talking a little bit about experiments. I'm going to be skipping over a lot of the details to kind of look at the big picture. But most of the experiments I'm going to be talking about are done in this kind of thing, where you have this kind of gold toothpaste tubes where you put in minerals in a solution that goes inside a pressure vessel, which then goes inside an oven and gets heated up over time. And one of the really good features about this is there's a little valve attached to this thing that you can monitor the fluid composition over time and measure things like hydrogen and methane, dissolved inorganic compounds. And then at the end of this experiment, you can take out the minerals and have a look at them. So here's just a quick overview of one of these experiments. So you start out with this nice naked olivine over there, cook it at 300 degrees for about 3 months, and it comes out covered with this nice hairy looking chrysotile mineral. And there's also brucite, magnesite in this particular experiment, and some hydrogen being produced. So here's a diagram showing the amount of hydrogen generation over elapsed time. And I've just noticed this, emphasizing on this scale here. So this is 1 year. So these are long-term experiments. So there's 3 experiments shown here. In the yellow triangles here is a reaction with orthopyroxene alone, just one of these components of these ultramafic rocks. And over several months reaction, this is a reaction that doesn't produce any hydrogen. In the blue boxes here is an olivine-only experiment, so there's only olivine in there, And it doesn't do much initially, but then starts producing hydrogen over this year reaction time. When you put those two things together, you get not much at the beginning, but then you see this big burst of hydrogen over time. So having both minerals in there together makes these both minerals react faster and produces more hydrogen. So just to look at that one experiment that produces this hydrogen, so this is olivine plus orthopyroxene reaction. At the beginning of this reaction, the orthopyroxene is reacting faster than the olivine, and it produces serpentine and talc as the primary minerals. And during this interval, it doesn't produce very much hydrogen. But then after a while, as the orthopyroxene goes away, the olivine becomes more important, and there's a shift in reaction pathway. So instead of producing serpentine and talc and not making much hydrogen, it shifts to a regime where it's making serpentine, brucite, and magnetite, and that produces hydrogen. So you're seeing a change in reaction pathway as this reaction proceeds. So you think, okay, well, you put orthopyroxene and olivine together, it makes a bunch of hydrogen. Well, maybe not. So here's another experiment here. So here's this orthopyroxene plus olivine experiment, the olivine-only experiment. And down here, this is a Harsberg experiment. So it has a little bit more orthopyroxene, a little bit higher orthopyroxene to olivine ratio than this experiment, but it also includes a little bit of clinopyroxene. And in about 10 months of reaction, that experiment produces no hydrogen. And it's not because the things aren't reacting. About 25% of that rock has reacted. It's serpentinized. Serpentine is really the only mineral produced in this experiment. There's no magnetite. So it's extensively altered, but it's not producing hydrogen. Another thing about these experiments, so one of the characteristics of low temperature serpentinites is highly alkaline pH. And the canonical view of how that comes about is you dissolve calcium-bearing pyroxenes, clinopyroxene, that goes into solution, consumes protons, or H+, releasing calcium into solution. And since calcium doesn't precipitate, then it drives the pH up. But this experiment went to a highly alkaline pH, didn't have a calcium-bearing mineral in there. The calcium concentration is low. This experiment had clinopyroxene in it, dissolved to make a bunch of calcium, yet the pH steadfastly remained at circumneutral pH. So if you saw this fluid coming out of the ground on the ocean floor that had a circumneutral pH, no hydrogen in it, you would not imagine that that rock had reacted with ultramafic rock and undergoing active serpentinization. So here's another set of experiments. So here's again this olivine plus orthopyroxene experiment, 230 degrees. This is an experiment done by Seefried et al. So they have a larzolite reacting at 200 degrees, so it has a little bit more clinopyroxene. And superficially here, it looks like the same sort of thing. Okay, so there's a little bit of lag in hydrogen production. Then hydrogen is being produced very much at a very similar rate to this, producing similar amounts of hydrogen. So they seem kind of similar, right? But these actually take very different reaction pathways to get this. So in this larzolite experiment, produces a bunch of ferric iron-rich serpentine and brucite and no magnetite, whereas this experiment produced iron-poor serpentine and brucite and tons of magnetite. So they're both producing lots of hydrogen, but they're doing it in very different reaction pathways to get there. So the hydrogen is, in this experiment, is coming from the Fe3 that's going into serpentine rather than production of magnetite. This experiment here would have no magnetic signature if you went to look for it on the seafloor, whereas this one would produce a very strong magnetic signature on the seafloor. So just one more of these experiments. So here's two experiments. Again, our olivine and orthopyroxene experiment is 230 degrees. See, if you do the exact same experiment, same ingredients, same methods at 265 degrees, it produces only serpentine and no hydrogen. So very different reaction pathways in different sort of circumstances. And so what I'm trying to convey here is that there's not just one reaction pathway that serpentine takes, or serpentinization takes, but it can be very many different reaction pathways, and they can have very different products. And exactly why that happens is not yet clear. But one thing that does come in if you're in a regime where pyroxene is reacting faster than your olivine, you typically produce serpentine and can produce little hydrogen. Whereas if you're in a regime, have circumstances where the olivine is reacting faster than pyroxene, then you get this more canonical set of serpentinite mineral assemblages and hydrogen production. Now, to some extent, this really matches what you predict from equilibrium, and thermodynamic equilibrium plays a significant role in that. So here's, I've shown on the left here is some equilibrium calculations as a function of temperature, what minerals you expect to get from serpentinization, going from an olivine-only situation to produce things that have higher amounts of orthopyroxene. So you go from a situation where you produce brucite, serpentine, and maybe magnetite to one that has less magnetite and brucite, and as you get more orthopyroxene, you get down here. But it's also clear that kinetics play a big role in this thing. It's not just being driven by thermodynamics. And it turns out, if you look in detail, a lot of the minerals within the experiment are not really in equilibrium with one another. The brucite is typically not in equilibrium with chrysotile. The magnetite is not in equilibrium with the brucite. And also, if you start out with your experiment with this kind of olivine orthopyroxene ratio, at the beginning it reacts like this, and in the end it reacts like this. So kinetics are a big driver for this. So we've also been looking at rates of these kind of things. So here's hydrogen as a function of temperature, hydrogen production as a function of temperature. 300 degrees, you get a lot of reaction. 265 is less. 230 degrees, even less hydrogen. And by the time you get to 200 degrees C, hydrogen production is so slow that you can't even measure it over year time spans in the lab. This is partly because the reaction is slowing down, but also because as you go down in temperature, iron is being forced into brucite rather than magnetite. So here's a compilation that I put together of all the currently available data on the rates of the serpentinization reactions. So up until a few years ago, the data that we had available were these sets of experiments here from the 70s and 80s, and those were used pretty much by most people to determine what the rates of this reaction were like. Everything we've done, as well as some recent experiments by Malvoisin et al., plot down here with much slower rates. And I think these are really the ones that are most representative of natural systems, and probably indicate that rates of this reaction are like 50 to 80 times slower than we thought of just a few years ago. And you'll notice there's no data down here. That's largely because as you go below temperatures of about 170 degrees, these reactions are just too slow to proceed on laboratory timescales. So now here's hydrogen generation from these from experimental studies, all the ones that are available. And so this is as a function of temperature, hydrogen production in nanomoles per gram per day. So here's a bunch of laboratory experiments, mostly at high temperatures. And I've drawn a little line there to kind of extrapolate down using Arrhenius kinetics down to lower temperature. One thing I haven't mentioned before is if you go up in pH, rates of reaction go up faster. So these open symbols are experiments at high pH. And you can see that there's a really, really rapid drop-off with lower temperatures. And these experiments down here, I've got arrows on these because these are all low-temperature experiments where the hydrogen generation was so slow that you really can't detect it from background. So these are all maximum values, and they're probably actually down here. But the point is that the hydrogen generation really drops off with temperature. So hydrogen generation is really slow once you get down to temperatures below about 100 degrees. So there's kind of this notion out here, particularly with these terrestrial serpentinizing systems, that you can have rainwater go into these systems and in relatively timescales of a couple years, go into these systems, react with the rock, and come out with an alkaline pH full of hydrogen and maybe methane. And I would say that the data that we have now tell us that this is not happening. It takes a long, long time for these fluids to go through here, react, serpentinize. Maybe time scales on the order of something like hundreds of thousands, or tens of thousands to 100,000 years when you get to these low temperatures to allow these reactions to go on. So when we're seeing these alkaline, hydrogen-rich fluids coming out of these terrestrial systems, I believe that those are fluids that are coming from deep in the systems that have been down there a long time or reached higher temperatures that are just coming up from the system rather than something that's short-term. So I just want to spend a couple of minutes here at the end talking about this carbon reduction in these systems. So there's been for a long time a notion that this hydrogen that's present in these systems can react with dissolved CO2 and produce things like methane and other organics. The problem is there is almost no evidence to support this now from experimentally. So over the years, there have been a number of laboratory studies that have reported the production of abiotic methane and other hydrocarbons from dissolved inorganic carbon during these experiments. And this is one of the first ones of this to report this from Mike Burntt's experiment in 1996. So he did a 300-degree reaction with olivine. Serpentinization produces a bunch of hydrogen. CO2 goes down, and we see a little bit of methane, ethane, and propane being produced, which was interpreted as coming from reduction to dissolved CO2. The problem is, whenever these experiments are done with a labeled, a C13 labeled carbon source that allows you to trace where the carbon is coming from, most of all of this carbon, these organic compounds, comes from background sources rather than reduction of dissolved CO2. So here's an experiment that I did back in 2001 with Jeff Seewald, where it duplicates essentially Burntt's experiments, only with a labeled CO2 source, and only a small amount of methane and none of these other hydrocarbons comes out C13. And I've repeated this with a number of other experiments, and paper published a couple years ago now, where all those experiments I showed earlier that produce all this hydrogen, we also take the methane out of those experiments. There's a bunch of methane being produced, but none of it comes out. So we put in this C13 labeled CO2 in these experiments, but all the methane that comes out of these experiments is C12. So it's not coming from reduction of the carbon that we put in there. It's from a background source. And I think this agrees very much with more recent, a lot of more recent experiments from natural systems, or results from natural systems. And overall, it tells us that reduction of CO2 to make things like methane and other organic compounds is really inhibited in these systems and maybe kinetically prohibited at temperatures below about 300 degrees. So just a couple implications for icy worlds. Serpentinization can follow many different pathways, some of which produce lots of hydrogen and alkaline pH, but others that don't. Reaction rates below about 100 degrees C are far too slow to serpentinize and produce hydrogen on short time scales, so fluids must be in these systems for long periods of time or reach higher temperatures to supply significant hydrogen to these environments. And I don't know what implications that might have for circulation in ocean worlds. Maybe things can persist in the mantles for a long time. And finally, so this abiotic reduction during serpentinization is unlikely to be responsible for methane and other organic compounds that are found in icy worlds, unless the temperature has gotten much higher than what we typically think of in these systems. But maybe this stuff comes from somewhere else rather than low temperature serpentinization reaction. That's it.
Time for a quick question.
That was an interesting talk, but I got confused somewhere, and I must have missed something. You said from olivine, hydrogen production decreases sharply with temperature.
Yes.
But then you had, right after that, you had a graph showing the rate of hydrogen production increasing with temperature. Was that from olivine or a different mineral? It seems like they're saying the opposite thing.
Like.
Yeah. There you see the hydrogen production increases with temperature, but in a few slides before that, you said that
no, hydrogen increases with. No, I'm sorry. Yes, no, it decreases with decreasing temperature. That's what. Yes, it always decreases with decreasing temperature.
Oh, so okay.
Sorry, I'm sorry. I must have. Yeah. Yeah, so it goes down as you decrease in temperature, the rate of hydrogen production goes down.
Okay, that's the thing that confused me.
Okay,
Okay.
sorry. I can see why you're confused.
We have to move on, but we can come. Oh, okay, sorry. Yep.
Just very quickly. So in your experiment, that tube that looked like a toothpaste tube, is a closed system. So you do not circulate the water in it, right?
Yes.
So what would you guess would happen if you actually keep circulating the fluid? So the whatever calcium that's been concentrated are just discharged, and will the result be anything different?
Well, I sort of view these experiments as being the accumulated results of fluid flowing through a system at relatively high water-to-rock ratios. And I think there would be some differences between, if you duplicated the natural system in terms of fluid flowing through these things. But I think the residence time, allows reactions to go on for a long time before it moves out of the system. So I don't think that things are going to be a lot different, somewhat different, but not a lot different. I don't think it necessarily I don't think it necessarily precludes the possibility that things never, reach that high pH as they're going through there. If that was your question, that the fluid flow would preclude that from happening. I don't know. It's hard to explain. It's hard.